It seems like a number of times in this course we'll have a section that is long, particularly complicated, maybe particularly important, maybe, and we'll follow it up with a section that is relatively short. Now, I'm not going to tell you the section is unimportant, but I'll tell you that it's a relatively short, sort of 3 slides. That seems to be something of a pattern for us. Okay, so we've talked about languages that are regular, languages that are accepted by some finite state machine, and we want to describe some of the properties of those languages. They have awful nice properties. Okay, so let's see here. So we're looking at a regular language is one that's recognized by a finite state machine, or equivalently, we saw with Kleene theorem, described by a regular expression. And just to to sort of put it in your mind, the language consisting of the strings a followed by some number of b's, where that number can be any number. So that's a set of strings a b, a b b, etc., etc., etc. is a regular language. And any finite set of strings is a regular language, because of course you could make a regular expression. Suppose you had the language was some finite set of strings. How about AB, BAB, and BBAB? Well, you could make the regular expression AB or BAB or BBAB. Whoops, lost my way. Here we go. Okay, so any finite set of strings is a regular language. So we're looking at a pretty big pile of languages. Okay, in the proof of Kleene's theorem, we saw that 2 languages are regular, then the union's also regular. Right? We also saw that 2 languages are regular, then the concatenation is regular. So we saw or, and we saw, we saw parallel, and we saw serial. We say that a structure is closed under an operation if performing an operation on the members always yields another member. Just as a very simple example, if you take numbers in the natural numbers and you double them, why then you always get a natural number. So performing the doubling operation keeps you inside the natural number, so the natural numbers are closed under the doubling operation. Natural numbers are not closed under the halving operation. If you take 3 and you halve it, you don't end up with a natural number. So closed is a useful property of structures. The collection of regular languages is closed under union, concatenation, and Kleene star. And the basic idea here is that in the first lemma for the proof of Kleene star, for the proof of Kleene's theorem, we did the regular expressions operations of pipe, concatenation, and Kleene star, and those correspond to of pipe, concatenation, and Kleene star, pipe, concatenation, and Kleene star. Here we go. Those correspond to the set operations. So for example, if R0 is a regular expression describing the language L0 and R1 describes L1, then the regular expression R0 pipe L1 describes L0 union L1. Okay, so we've really already, this lemma is just a reminder of something that we've already talked about. Okay, so next up is the collection of regular languages is closed under set complement, intersection, and set difference. So we're looking at languages are sets of things, so we're looking at what's the interaction between set operations and languages. It's a very natural thing to do. So we want to do set complement, intersection, and set difference. So we're going to first observe something, that the identity here, the identity that S intersect T, this is a set identity. Has nothing to do with languages, has to do with sets. S intersect T is S complement union T complement, complement. So S intersect T is S complement union T complement, complement. Gives the intersection in terms of union and complement. And I thought that I could draw a Venn diagram. We'll see how we do. See how we do. I'm not gifted at drawing. You know that. So I've got S and T. I've got S and T. Okay, so I'm going to plunge in here. I'm looking for the intersection right there. You know where the intersection is. So I'm going to take S complement, all this stuff, 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 S complement, and maybe I'll switch to a different color. I'll be bold and switch to a different color. And T complement, see how I do with T complement, all this stuff, all this stuff, all this stuff, all this stuff, all this stuff. There we go. That's S complement in green and T complement in red. Ooh, the red is giving me the heebie-jeebies. S complement in green and T complement in red. And which parts don't get crossed out in either green or red? And the answer is just that little part there. So S intersect T is S complement union T complement complement. So it gives the right-hand side describes the intersection in terms of union and complement. The prior lemma says that regular languages are closed under union, so if we show that they're closed under complement, then we've done intersection. Okay. Similarly, S take away T is S union T complement, so if we show closure under complement, that will also show closure under set difference. Okay, so we're leveraging previous work, which is why we included the previous work on the prior slide. You might have said, well, we already did that. Why did we do it twice? Well, because we want to use that right now. So to show that a complement of a regular language is also regular, I'm going to fix a regular language over some alphabet. It's recognized by some deterministic finite state machine M. I mean, you see where I'm going with this. And I'm going to define a new machine that'll recognize the complement language, so I must have to fiddle with the original machine somehow. So the new machine will have the same states and the same transitions. But what you do is you flip it so that what used to be an accepting state is now not an accepting state, and what used to be not an accepting state is now an accepting state. So the final states get flipped. And all we got to remark then is that the language of this machine is the complement of the original language. Language of this machine is the complement of the original language inside the universe of sigma star. Okay, so because M is deterministic, each input string is associated with a unique last state. That was the whole point of delta hat. Okay, the whole point of delta hat is that it tells you what is the last state. Well, then you just observe that delta hat of tau is one of the final states of M hat, if and only if delta hat of tau is one of the final states of M hat, if and only if delta hat of T is not in one of the final states of M. That's all, because you flipped them all. So the language of M hat is the complement of the language of M, and so we're done. Okay, so we leverage this elementary set, somewhat obscure set equality to get that what we needed from just set complement. Okay, and 3 examples to finish this off. Okay, so I'm going to take the alphabet to be 0, 1, the regular the bit strings. So I'm going to be looking at languages of bit strings just for variety. We looked at A's and B's. Now we're looking at bit strings just to do something different. So we're going to look at the set of all strings that end in 1. Bit strings that end in 1. That's what this is. These are bit strings that end in 1. Okay, I could show it's regular by producing a finite state machine. Great. You could do a deterministic one. You could do a non-deterministic one. Great, 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 great. Or you could show that it's regular by giving a regular expression that describes it, because that's what Kleeni's theorem says. That's an alternative to show that it's regular. But we can also use the closure operation that we've just been talking about. Okay? So the language that we've got up here, the language of strings that end in the language of strings that end in 1, is the concatenation of L0 and L1, where L0 is all strings and L1 is the clearly regular language consisting of just a single string which has just a single character 1. Okay, and that's regular for many reasons, but one is that you can easily write down the regular expression to describe it. The regular expression capital R equals 1. That's it. Okay, this is the concatenation of 2 regular languages. We know that regular languages are closed under concatenation, so we're done. So studying what regular languages do in terms of set operations and in many other ways gives us some insight into what's going on. Just again, 2 more examples just to try to illustrate really what's the point of this particular study. Okay, so this language here is the set of strings over the alphabet is A, B, C, the character A, the single character B, and the single character C. And so the strings are A, B, C, the cleaning star of A, B, C. Sigma does not have the substring A, C, B. Does not have the substring A, C, B. So again, you could try to make a finite state machine, either deterministic or non-deterministic, to act that way. You can try to make a regular expression that describes this, or another thing you could do is you could say it's the complement of the set of strings that do have the substring ACB. And do have the substring ACB is clearly a regular language. You can easily, for example, write down a deterministic finite state machine. You can easily, very easily, write down a non-deterministic finite state machine, and you can also write down a regular expression. I happen to have written down the regular expression, but I could have drawn the finite state machine. It wouldn't have been very hard at all. So it's some stuff followed by ACB followed by some stuff. That's the complement of the given language, of the language that is in some sense the problem here. Well, but regular languages are closed under complement. So if you know that the complement is a regular language, then the language itself is also regular. Okay, so these operations, studying these set operations on regular language does give a person some insight into what's happening. Okay, one more, and then we'll call it a day. So we're going to show that the language here of strings over AB that contain both of the substrings ACB and CBC is regular. And again, you can imagine constructing a finite state machine. You can imagine giving a regular expression, but we're going to do the following. We're going to say I can obviously make a finite state machine that accepts strings that have a substring of ACB. A non-deterministic finite state machine is very easy. You could also describe it with a regular expression. Anyway, any of those choices. So substring of ACB, that's a regular language. Substring of CBC, that's a regular language. Regular languages are closed under intersection, so you're done. And really, trying to make a finite state machine to do this job is at least slightly intricate. And as an argument that trying to make a finite state machine to do this job is at least a little intricate, I'll point out that ACBC is a member of L. That 4-character string is a member of L because it has the substring ACB. It also has the substring CBC. So if you were trying to make a finite state machine to recognize containing both the substrings ACB and the substring CBC, you'd have to worry about what if they overlap. Okay, so there's something to worry about, but this argument right here, the argument that uses the closure of regular languages, very slick, very fast, very easy. Okay, very good. So like I said, a relatively short one today, which is always nice.